Hello, everyone. Today we're going to continue the discussion of a limit. We're going to discuss one-sided limits and continuity in 2.5. As we discussed before, limit is the value a function approaches when x approaches a. So if we consider the function on both sides of a, then it can approach different values. Then we have the concepts of one-sided limits in this case, like in the following example. I suppose f(x) is a piecewise defined function where it's defined as x minus 1 if x less than 0, and it's defined as x plus 1 if x greater than or equal to 0. So this is a typical piecewise defined function. There are two pieces for the function. If you graph it, one piece is on the left side, then one piece is on the right side. In each piece, we see a straight line with slope 1, but they are shifted by 2 units from left to the right. By the way, on the left side, the boundary at x equal to 0 is not included, so we use an open circle. And on the right side, the boundary of x equal to 0 is included in the definition, so we use a solid point. So if you draw the lines or arrows on each piece, when you try to find the limit of the function as x approaches 0, then you see they approach different values from the two sides. And we have different side limits in this case. For example, as x approaches 0 from the right, f(x) approaches 1. So we call that the right-hand side limit. f(x) is 1, and we write the limit of f(x) as x approaches 0 plus equals 1. So we use the plus sign at the shoulder of 0 to denote it's the right side limit. Similarly, as x approaches 0 from the left, f(x) approaches negative 1 from the graph. We call that the left-hand side limit of f(x) is negative 1, and we write limit of f(x) as x approaches 0 minus on the shoulder equals to negative 1. So you can see, for the function to have a limit at x equal to 0 or any point, the left side limit and the right hand side limit have to be the same. So this gives us the following theorem. The theorem says the limit of f(x) as x approaches a equals L if and only if the limit of f(x) as x approaches a from the left equals L, and the limit of f(x) as x approaches a from the right equals L. So that means the left hand and right hand side limits of the function both need to exist and they need to be the same. So this is about the one-sided limits, and now we're going to talk about continuous functions. We have learned the continuous functions before in pre-cal, but we have learned the concepts of limits. So we can use the language of limit to define a continuous function. And a function f(x) is continuous at x equal to a if the following 3 conditions are met. Condition 1, f of a is defined. Condition 2, the limit of f(x) as x approaches a exists. And condition 3, the limit of fx as x subtract a is equal to f of a. Okay, we're going to look at an example to illustrate this definition. So on the graph, you can see we have a function f, and it has several pieces. And in each piece, we even have some broken point or open circle. So obviously, the function is not continuous at those places. We have 4 different situations in here. When x is equal to a, obviously the function is not continuous. If we use the definition in here, we see that the condition 1 is not satisfied. F of a is not defined because there is an open circle on the curve. That means the function is not defined at x equal to a. At x equal to b, the function is defined. That is the closed points on the top. But this function is still not continuous because condition 3 is not satisfied. The limit exists in this case, which is the open circle, but it does not meet with the function value of the closed circle. So the function is not continuous. At x equal to c, we have another situation where the function is not continuous. In this case, the limit does not exist at x equal to c. You can see the left hand side limit and the right hand side limit are different. So condition 2, the limit exists is not satisfied. Obviously, because of that, condition 3 is also not satisfied. At x equal to d, obviously, we got all the conditions unsatisfied. F of a is not defined. This curve has the asymptote at x equal to d, and the limit does not exist. The 2 curves keeps going up or down without bound, and consequently, condition 3 is not satisfied also. Okay, so for continuous functions, we have an important theorem called intermediate value theorem. The theorem says, let f(x) be continuous on a closed interval from a to b. So we got a continuous curve in the graph. And the m is any number between f of a and f of b. Okay, so I just draw the graph of f in the diagram. And the fa is at the bottom, fb is on the top. So these are the 2 points on the curve. M is any number between f of a and f of b. Okay, for example, as the red line indicates, then it says there exists at least one number c in the interval from a to b such that f of c equal to m. So that says if you draw a horizontal line across m on the y-axis, it will intersect the curve at least once between a and b. And that's indicated in the graph also by the red lines. Okay. So one of the important applications of intermediate value theorem is to find the numerical solution of some equations. So in the next example, let's use this theorem to show that there exists a number x such that the function vanishes at that point. The function in the example is f equals x cubed plus x plus 1. And we need to show that there exists a number c between -1 and 1 such that f of c equal to 0. So what we do is we just define a to be -1 and b equal to 1 and m equal to 0. Then we evaluate f of a, which is f of -1. So plugging in -1 for x, we get the -1 cubed plus -1 plus 1. And you simplify it, you get -1. We can also evaluate f of b, which is f of 1. So that's equal to 1 cubed plus 1 plus 1. That's equal to 3. Okay, so remember m is equal to 0. So that's between -1 and 3. So by the intermediate value theorem, there exists a number c in the interval from -1 to 1 such that f of c equal to m equal to 0. Okay, so we can guarantee there is a solution to the equation of x cubed plus x plus 1 in this example, although we don't know what the exact solution is. And this has important applications in numerical computation and solving equations numerically. So we're going to continue next time on 2.6.